Welcome to an extraordinary journey through time and space. Tonight, we will witness the complete story of Mercury, our solar system's innermost planet. From its violent birth in the cosmic furnace surrounding our young sun, to the barren, cratered world we observe today, 4.5 billion years ago, in the swirling disk of dust and gas that surrounded our newborn star, the materials that would become Mercury began their fateful dance with gravity and heat. What followed was an epic tale of survival against impossible odds, a world forged in fire and sculpted by cosmic violence. From its oversized core to its ancient scarred surface, from scorching days to frozen nights, this is the complete timeline of Mercury. Prepare to witness 4.5 billion years of planetary history unfold in the most extreme environment of our inner solar system. Our journey to the closest world to our sun begins now. From its oversized core to its ancient scarred surface, from scorching days to frozen nights, this is the complete timeline of Mercury. Prepare to witness 4.5 billion years of planetary history unfold in the most extreme environment of our inner solar system. Our journey to the closest world to our sun begins now. Sit back, relax, and space out with me as we go through the entire timeline of the planet Mercury. Leave a comment of where you are in the world and what time it is. I would love to see where everyone is from. We begin our journey in the inner regions of the early solar system, where temperatures soar beyond the melting point of most materials. Here, within the blazing heat of our young sun's vicinity, the story of Mercury begins in conditions so extreme they challenge our understanding of planetary formation. The solar nebula surrounding our newborn star is not uniform in its composition. In these inner regions, only the most heat-resistant materials can survive. Metals like iron and nickel, along with rocky silicates that can withstand temperatures exceeding 1,500 degrees Celsius. Lighter materials, water, methane, ammonia, are blown away by intense solar radiation and stellar winds. In this furnace-like environment, particles of metal and rock begin their gravitational dance. Iron droplets, condensing from vapor in the slightly cooler regions, stick together with bits of rock and other refractory materials. These early building blocks are denser and more metal-rich than anything forming in the cooler outer regions where the gas giants will eventually take shape. In this furnace-like environment, particles of metal and rock begin their gravitational dance. Iron droplets, condensing from vapor in the slightly cooler regions, stick together with bits of rock and other refractory materials. These early building blocks are denser and more metal-rich than anything forming in the cooler outer regions where the gas giants will eventually take shape. The process of accretion proceeds differently here than in the outer solar system. The intense heat means that only the most heat-resistant materials participate in planet formation. As these metallic and rocky particles collide and stick together, they create objects with much higher metal content than planets forming further from the sun. Over millions of years, these dense aggregations grow larger through continued collisions. The early planetesimals in Mercury's orbital zone are bombarded constantly by debris, but they also grow through gravitational attraction of additional material. Each impact adds mass while also generating enormous amounts of heat through the conversion of kinetic energy. But Mercury's formation story takes a dramatic turn that will define its character forever. As the young planet grows to perhaps twice its current size, with a substantial rocky mantle surrounding its iron core, catastrophe strikes in the form of a massive collision. A Mars-sized object traveling at incredible velocity slams into the growing planet. The impact is so violent that it strips away most of Mercury's rocky outer layers, leaving behind primarily the dense iron core. This catastrophic collision explains Mercury's unusual composition. It is nearly 75% iron by mass. giving it the largest metallic core relative to its size of any planet in our solar system. The collision also imparts additional angular momentum to Mercury, affecting its rotation rate and potentially contributing to the unusual orbital characteristics it will develop. The debris from this impact either escapes Mercury's weak gravitational field or falls back to the surface, creating additional cratering and contributing to the planet's battered appearance. In the aftermath of this great collision, Mercury continues to grow through the accretion of remaining debris in its orbital zone. But now it is fundamentally different from what it might have been. A world dominated by its metallic core, with only a thin rocky shell surrounding the dense interior. The intense heat from the nearby sun ensures that any volatiles, water, atmospheric gases, organic compounds, are immediately boiled away into space. Mercury's weak gravity, a consequence of its relatively small size despite its high density, cannot retain these materials even if they somehow survive the thermal assault. As the early bombardment period continues, Mercury's surface becomes increasingly cratered. Unlike the outer planets, which will eventually develop thick atmospheres that can burn up incoming meteors, Mercury remains essentially airless, allowing every impact to reach its surface and create permanent scars. The young sun itself contributes to Mercury's harsh conditions. In its youth, stars often experience periods of increased activity. Solar flares, coronal mass ejections, and enhanced stellar winds that would strip away any atmosphere Mercury might attempt to develop. The combination of proximity and stellar youth ensures that Mercury remains a bare rock in space. During this violent early period, Mercury's interior begins differentiating. The massive iron core, heated by radioactive decay and continued impacts, remains partially molten. This creates the conditions for Mercury's weak but measurable magnetic field, a remnant of more active geological processes that occurred when the planet was young. The surface temperature variations that will characterize Mercury throughout its history are established during this early period. With no atmosphere to distribute heat, areas facing the sun experience temperatures hot enough to melt lead, while regions in permanent shadow remain frozen at temperatures approaching absolute zero. As we move forward through this early epoch, Mercury settles into the orbital and rotational characteristics that will define it for the rest of solar system history. Its highly elliptical orbit brings it as close as 46 million kilometers to the Sun and carries it as far as 70 million kilometers away, creating dramatic seasonal variations in the intensity of solar heating. The planet's rotation becomes locked in a 3:2 resonance with its orbit, rotating 3 times for every 2 trips around the Sun. This unusual relationship means that Mercury's day is actually longer than its year, creating complex patterns of heating and cooling across the planetary surface. Moving forward through Mercury's early history, we enter a period of unprecedented violence across the entire inner solar system. The late heavy bombardment transforms Mercury's surface into a landscape that will preserve the scars of this cosmic assault for billions of years. During this era, the gravitational interactions of the giant planets in the outer solar system destabilize countless asteroids and comets, sending them careening through the inner solar system. Mercury, with its position closest to the Sun and its lack of protective atmosphere, bears the brunt of this cosmic shooting gallery. The impacts during this period are unlike anything in Mercury's previous experience. Asteroids tens of kilometers across strike the planet's surface at velocities exceeding 60 kilometers per second. Each collision releases energy equivalent to millions of nuclear weapons, vaporizing both the impactor and vast quantities of Mercury's crustal material. The largest of these impacts creates the Caloris Basin, a massive crater over 1,500 kilometers in diameter. The collision that forms this basin is so violent that it sends shockwaves completely through Mercury's interior, creating strange terrain formations on the opposite side of the planet called weird terrain. a jumbled landscape of hills and valleys created by the focusing of seismic energy from the antipodal impact. The Caloris impact represents one of the most significant single events in Mercury's geological history. The asteroid responsible was likely over 100 kilometers in diameter, and its collision excavated material from deep within Mercury's crust. The impact basin becomes surrounded by concentric rings of mountains thrust upward by the tremendous forces involved. But Caloris is only the largest of countless impacts during this period. Mercury's surface accumulates craters of every size, from tiny pits created by sand grain-sized particles to massive basins hundreds of kilometers across. Each impact adds to the planet's heavily cratered appearance and contributes to the pulverized regolith that will cover much of its surface. The bombardment has profound effects on Mercury's internal evolution. The constant impacts keep the planet's interior heated through the conversion of kinetic energy to thermal energy. This enhanced heating contributes to continued geological activity, including volcanism that begins to modify the heavily cratered terrain. Volcanic activity during this period takes forms adapted to Mercury's unique conditions. With no atmosphere to interact with, volcanic eruptions occur in the vacuum of space. Lava flows spread across the surface in sheets, filling some of the smaller craters and creating the smooth plains that contrast with the heavily cratered highlands. The volcanic rocks that form during this period are primarily basaltic, similar to the Maria on the Moon, but formed under the more extreme conditions near the Sun. These lavas are probably generated by partial melting in Mercury's mantle, driven by the heat from continued impacts and radioactive decay of elements in the planet's interior. Mercury's magnetic field, generated by convection in its large iron core, reaches its peak strength during this period. The combination of rapid rotation, a molten outer core, and continued heating from impacts creates conditions favorable for generating a strong dynamo-magnetic field that extends far into space around the planet. This magnetic field begins to interact with the solar wind, the stream of charged particles flowing outward from the Sun. Even at this early stage, the solar wind near Mercury is much more intense than in the outer solar system, creating a dynamic magnetosphere that deflects some particles while allowing others to impact the surface directly. The interaction between Mercury's magnetic field and the solar wind creates the first hints of the planet's thin exosphere, an extremely tenuous envelope of atoms knocked from the surface by solar wind bombardment and micrometeorite impacts. This exosphere contains sodium, potassium, calcium, and other elements liberated from the rocky surface. As the bombardment continues, Mercury's surface temperature regime becomes well established. The lack of atmosphere means that surface temperatures are determined entirely by solar heating and the planet's own thermal radiation. Daytime temperatures soar above 800 degrees Celsius, while nighttime temperatures plummet to minus 170 degrees Celsius. These extreme temperature variations create thermal stresses in Mercury's crustal rocks that contribute to their breakdown and modification over time. The repeated heating and cooling cycles cause rocks to expand and contract, creating fractures and contributing to the gradual erosion of crater rims and other surface features. During the most intense phases of bombardment, Mercury's surface undergoes continuous modification. No sooner do volcanic flows create smooth plains than new impacts crater them again. The planet's surface becomes a palimpsest, a document that has been written on, erased, and rewritten countless times throughout its history. Some of the impact basins created during this period become filled with later volcanic deposits, creating the smooth plains that will be among Mercury's most distinctive surface features. These plains represent some of the youngest terrain on the planet, though young in this context still means billions of years old. The bombardment also affects Mercury's orbital evolution. Large impacts can slightly alter a planet's rotation rate and orientation. Though Mercury's proximity to the Sun means that tidal forces quickly restore its spin-orbit coupling. The planet settles into its unusual 3-to-2 resonance, where it rotates exactly 3 times for every 2 orbits around the Sun. As we move toward the end of this bombardment era, Mercury has acquired most of the surface features that will characterize it for the rest of solar system history. The major basins are in place, the volcanic plains have formed, and the planet has settled into the thermal and dynamical state that will persist for billions of years. The stage is now set for a much longer period of more gradual change, as Mercury transitions from a world shaped by catastrophic events to one modified primarily by the slow but persistent effects of solar heating, thermal cycling, and the gradual reign of smaller impactors. As the era of heavy bombardment draws to a close, Mercury enters a period characterized by extensive volcanic activity that will fundamentally alter portions of its surface. The transition is gradual rather than abrupt, with large impacts becoming less frequent, while internal heat sources drive continued geological activity. The volcanic activity during this period is powered by several heat sources working in combination. Radioactive decay of elements like uranium, thorium, and potassium within Mercury's interior continues to generate significant heat. Additionally, the gravitational energy released by the continued differentiation of Mercury's core contributes to mantle melting. But Mercury's volcanism is unlike that on any other terrestrial planet. The extreme proximity to the Sun creates unique conditions for volcanic processes. Lava erupted onto Mercury's surface must contend with dayside temperatures already exceeding 700 degrees Celsius, while nightside eruptions encounter surface temperatures below -150 degrees Celsius. These temperature extremes affect how volcanic materials behave once they reach the surface. On the day side, lava flows can remain molten for extended periods, allowing them to travel great distances and create extensive sheet-like deposits. The lack of atmosphere means there is no convective cooling, so heat loss occurs only through radiation and conduction to the underlying surface. On the night side, the situation is dramatically different. Lava erupted into the frigid environment loses heat rapidly to the cold surface and through radiation to space. This rapid cooling can create distinctive volcanic textures and may lead to the explosive fragmentation of lava as thermal stresses build up within cooling flows. The most extensive volcanic activity occurs in and around the major impact basins created during the previous bombardment period. The Caloris Basin becomes a focus for volcanic activity as deep fractures created by the original impact provide pathways for magma to reach the surface. Successive volcanic eruptions gradually fill portions of the basin with smooth plains deposits. These smooth plains represent some of Mercury's most geologically young terrain, though they are still billions of years old. The plains are characterized by their relatively low crater density compared to the heavily cratered highlands, indicating they formed after the most intense period of bombardment had ended. The composition of Mercury's volcanic rocks reflects the planet's unique bulk composition and formation history. With such a large iron core relative to its silicate mantle, Mercury's lavas are enriched in certain elements compared to volcanic rocks on other planets. They contain higher concentrations of sulfur and lower concentrations of iron than typical basalts, reflecting the specialized conditions in Mercury's mantle. Volcanic eruption styles on Mercury are constrained by the lack of volatiles. Without water or other volatile components, Mercury's magmas cannot generate the explosive eruptions common on Earth. Instead, volcanism consists primarily of effusive eruptions that produce extensive lava flows and sheet-like deposits. The volcanic plains often display distinctive ridge systems, long, linear features that reflect tectonic stresses within Mercury's crust. These ridges form as the volcanic plains cool and contract, creating compression features that can extend for hundreds of kilometers across the planet's surface. During this period, Mercury's magnetic field continues to be generated by convection in its large iron core. The magnetic field interacts with volcanic processes in subtle ways, potentially affecting the movement of any electrically conducting materials within volcanic flows, though these effects are much less dramatic than the magnetic interactions observed on more volcanically active worlds. The interaction between Mercury's magnetosphere and the solar wind becomes increasingly important during this period. The solar wind near Mercury is far more intense than in the outer solar system, with particle densities and velocities that create a highly dynamic interaction with the planet's magnetic field. This interaction contributes to the continued development of Mercury's exosphere through a process called sputtering. High-energy particles from the solar wind strike Mercury's surface and knock atoms free, creating the tenuous envelope of gases that surrounds the planet. The composition of this exosphere reflects the surface composition, containing sodium, potassium, calcium, and other elements. Volcanic outgassing also contributes to Mercury's exosphere, though the contribution is minimal compared to sputtering processes. Any gases released during volcanic eruptions are quickly lost to space due to Mercury's weak gravity and the intense solar radiation that ionizes atmospheric particles and accelerates their escape. The volcanic plains period sees the establishment of Mercury's distinctive geological provinces. The heavily cratered terrain represents the most ancient parts of the planet's surface, while the smooth plains mark areas that were resurfaced by volcanic activity after the end of heavy bombardment. Between these extremes, intermediate terrain shows the effects of both impact cratering and volcanic modification. Some areas display partially buried craters, where volcanic flows have filled crater floors while leaving rims exposed. Other regions show evidence of volcanic flows that were subsequently modified by later impacts. The thermal environment during this period creates unique conditions for rock weathering and modification. The extreme day-night temperature variations cause thermal fatigue in surface rocks, gradually breaking them down into smaller fragments. This process is enhanced by the lack of atmosphere, which means there are no moderating effects from wind or weather patterns. Solar radiation during this period is intense enough to cause chemical changes in surface materials through processes similar to those observed on the Moon. Solar wind particles implant themselves in surface grains, while ultraviolet radiation breaks chemical bonds and creates new mineral phases that are stable only under the extreme conditions near the Sun. As volcanic activity gradually wanes toward the end of this period, Mercury's surface begins to take on the characteristics that will define it for the rest of solar system history. The major geological provinces are established, the thermal regime is well developed, and the planet settles into a more quiescent phase dominated by impact cratering and thermal modification. The transition from active volcanism to relative quiescence marks a fundamental change in Mercury's evolution. No longer is the planet's surface being continuously modified by internal geological processes. Instead, it becomes primarily a passive recorder of external influences, impacts, solar radiation, and the gradual effects of thermal cycling. This transition sets the stage for the next major phase of Mercury's history, when gradual cooling and contraction will create the distinctive tectonic features that make Mercury unique among the terrestrial planets. As Mercury's volcanic period comes to an end, the planet enters a phase of evolution that will create some of its most distinctive geological features. The transition marks the beginning of global cooling and contraction that will fundamentally alter Mercury's surface geology through tectonic processes unlike those operating on any other terrestrial planet. The cooling begins as Mercury's internal heat sources gradually diminish. Radioactive decay continues, but at reduced rates as the most rapidly decaying isotopes are depleted. The heat generated by continued core differentiation decreases as Mercury's interior reaches a more stable configuration. Most significantly, the cessation of major volcanic activity eliminates a primary mechanism for transporting heat from the interior to the surface. As Mercury's interior cools, the planet begins to contract. This contraction occurs because most materials occupy less volume when cooled, and Mercury's interior, dominated by its massive iron core, is no exception. The cooling and solidification of portions of the outer core cause the entire planet to shrink, though the process occurs over hundreds of millions of years. The surface expression of this global contraction takes the form of thrust faults and lobate scarps, curved cliff-like features that can extend for hundreds of kilometers across Mercury's surface. These features form when the planet's shrinking interior forces the rigid outer crust to accommodate a smaller circumference by folding and faulting. The surface expression of this global contraction takes the form of thrust faults and lobate scarps, curved cliff-like features that can extend for hundreds of kilometers across Mercury's surface. These features form when the planet's shrinking interior forces the rigid outer crust to accommodate a smaller circumference by folding and faulting. The lobate scarps are among Mercury's most distinctive geological features. They typically rise several hundred meters above the surrounding terrain and show clear evidence of compression. Craters and other surface features are often cut by these scarps, providing clear evidence that the contraction occurred after the major bombardment period and after most volcanic activity had ceased. The formation of these tectonic features requires significant stress levels within Mercury's crust. As the planet contracts, compressive stresses build up until they exceed the strength of crustal rocks, causing them to fail along thrust fault systems. The scarps represent the surface expression of these deep crustal faults. Some of the largest scarp systems extend for over 500 kilometers and show vertical offsets of more than a kilometer. These massive features indicate that Mercury has undergone substantial global contraction. Estimates suggest the planet's radius has decreased by several kilometers since the scarps began forming. The timing and distribution of scarp formation provide insights into Mercury's thermal evolution. The scarps cut across both heavily cratered terrain and smooth volcanic plains, indicating that contraction continued well after volcanic activity ceased. The global distribution of scarps suggests that contraction affected the entire planet rather than being localized to specific regions. Mercury's unusual orbital characteristics influence the distribution and orientation of tectonic features. The planet's highly elliptical orbit and 3-to-2 spin-orbit resonance create complex patterns of tidal stress that interact with the global contraction stresses. Some tectonic features show preferred orientations that may reflect this tidal influence. The formation of lobate scarps represents only the most visible aspect of Mercury's global contraction. The process also affects the planet's internal structure, potentially influencing the generation of its magnetic field. As the core cools and contracts, convection patterns change, which may explain variations in magnetic field strength over time. The formation of lobate scarps represents only the most visible aspect of Mercury's global contraction. The process also affects the planet's internal structure, potentially influencing the generation of its magnetic field. As the core cools and contracts, convection patterns change, which may explain variations in magnetic field strength over time. During this period, Mercury's exosphere becomes increasingly important as a record of surface processes. The tenuous atmosphere, maintained by sputtering from solar wind bombardment and thermal desorption from solar heating, provides information about surface composition and the rate of various space weathering processes. The interaction between Mercury's magnetosphere and the solar wind continues to evolve during this period. Changes in the magnetic field strength and configuration affect how solar wind particles interact with the surface, potentially influencing the rate of sputtering and the composition of the exosphere. The interaction between Mercury's magnetosphere and the solar wind continues to evolve during this period. Changes in the magnetic field strength and configuration affect how solar wind particles interact with the surface, potentially influencing the rate of sputtering and the composition of the exosphere. Impact cratering continues throughout this period, but at much reduced rates compared to the early bombardment era. The craters formed during this time often show distinctive characteristics related to Mercury's thermal environment and tectonic activity. Some craters are modified by scarp formation, while others preserve pristine morphologies in areas of relative tectonic stability. The thermal cycling that characterizes Mercury's surface environment continues to play a role in modifying geological features. The extreme day-night temperature variations cause repeated thermal expansion and contraction of surface materials, gradually breaking down crater rims and other topographic features through thermal fatigue. Solar wind bombardment during this period creates increasingly complex effects on Mercury's surface composition. The high-energy particles not only sputter atoms from the surface, but also implant foreign ions and create new mineral phases through radiation damage. Over time, these processes create a regolith layer with distinctive properties, unlike those found on other planets. The lack of atmosphere ensures that all of these surface modification processes operate directly on the exposed bedrock and regolith. There are no weathering processes involving liquid water, wind erosion, or atmospheric chemical reactions. Instead, space weathering dominates, creating surface materials with unique optical and chemical properties. As Mercury's global contraction continues, some regions experience more complex tectonic histories than others. Areas where multiple scarp systems intersect show evidence of complex stress patterns and multiple episodes of fault reactivation. These regions provide the most detailed records of Mercury's ongoing tectonic evolution. The planet's magnetic field continues to be generated by convection in its iron core, though the field strength may vary as the core's thermal and compositional structure evolves. The magnetic field plays an important role in deflecting some solar wind particles, while channeling others toward the polar regions, creating complex patterns of surface bombardment. Mercury's exosphere during this period shows seasonal variations related to the planet's elliptical orbit. When Mercury is closest to the Sun, increased solar heating enhances thermal desorption of surface atoms, temporarily thickening the exosphere. During more distant parts of the orbit, the exosphere becomes more tenuous as surface temperatures decrease. The formation of lobate scarps also affects local thermal environments by creating topographic shadows and areas of enhanced solar heating on south-facing slopes. These microclimates influence local space weathering rates and may contribute to compositional variations observed in different regions of Mercury's surface. As we move toward the end of this contraction period, Mercury has acquired most of the major geological features that characterize its surface today. The planet has evolved from a world dominated by impact cratering and volcanism to one shaped primarily by global tectonic processes and the ongoing effects of space weathering. The stage is now set for the final major phase of Mercury's geological evolution, a long period of relative quiescence, during which gradual processes slowly modify the surface features created during earlier, more dramatic periods of planetary evolution. As we continue our journey through Mercury's timeline, the planet enters its modern configuration, a phase that has persisted for billions of years and continues today. This era is characterized by the gradual modification of existing geological features rather than the creation of fundamentally new terrain types. Mercury has settled into a thermal and dynamical state that represents a balance between various competing processes. The planet's interior has largely finished differentiating, with a massive iron core that may be partially solid and partially liquid, surrounded by a thin silicate mantle and an even thinner rocky crust. The magnetic field generated by Mercury's core continues to operate, though at a much weaker level than the magnetic fields of Earth or the giant planets. This weak but persistent magnetic field creates a small magnetosphere that interacts with the intense solar wind environment near the Sun, providing some protection for the surface while also channeling charged particles toward the polar regions. During this modern era, impact cratering continues, but at very low rates. The solar system has largely cleared itself of the debris that created the heavily cratered surfaces we see today. New impacts are relatively rare events, but when they do occur, they create fresh craters that stand out against the ancient, space-weathered background terrain. The fresh craters formed during recent geological time show distinctive characteristics that help scientists understand Mercury's surface properties. They often display bright ray systems, streaks of fresh material excavated from beneath the space-weathered surface layer. These rays gradually fade over time as space weathering darkens the freshly exposed material. Space weathering processes continue to modify Mercury's surface throughout this period. Solar wind sputtering removes atoms from the surface and implants foreign ions. Micrometeorite bombardment continuously breaks down surface materials into finer particles. Solar ultraviolet radiation and X-rays cause chemical changes in surface minerals. The combination of these space weathering processes creates a unique surface environment found nowhere else in the solar system. Mercury's proximity to the Sun means that solar wind densities are much higher than at Earth's distance, while the lack of atmosphere ensures that all space weathering processes operate directly on the surface materials. Mercury's exosphere evolves continuously as a result of these surface interactions. The tenuous envelope of sodium, potassium, calcium, and other atoms is constantly replenished by sputtering and thermal desorption, while being lost through photoionization and subsequent acceleration by the solar wind. This creates a dynamic equilibrium that varies with Mercury's orbital position and solar activity levels. The planet's unusual orbital characteristics continue to create complex thermal environments. The 3-to-2 spin-orbit resonance means that some regions experience different thermal histories than others. Areas near the subsolar points at perihelion experience the most extreme heating, while regions near the terminator experience more moderate temperature variations. These thermal differences contribute to regional variations in space weathering rates and surface composition. Areas that experience the most extreme heating show enhanced thermal desorption of volatile elements, while cooler regions may retain more of their original composition over longer time periods. During this era, Mercury's polar regions acquire special significance due to their unique thermal environment. Areas in permanent shadow near the poles may be cold enough to trap water ice and other volatile materials delivered by cometary impacts. These cold traps represent some of the most extreme environments in the inner solar system. The discovery of these polar deposits awaits the space age, when Earth-based radar observations and eventually spacecraft missions reveal the presence of highly reflective materials in permanently shadowed crater floors near Mercury's poles. The deposits are likely composed primarily of water ice, with possible contributions from other volatiles like sulfur compounds. The modern era also sees the continuation of Mercury's global contraction, though at much reduced rates compared to earlier periods. New lobate scarps may still be forming as the planet's interior continues to cool and contract, though the process is now much slower than during the major scarp-forming period billions of years ago. Tidal forces from the Sun continue to stress Mercury's crust as the planet follows its elliptical orbit. The changing distance from the Sun creates periodic variations in tidal stress that may trigger small amounts of seismic activity, though Mercury's seismic activity is likely much lower than that of more geologically active planets. The planet's magnetic field continues to interact with the solar wind, creating phenomena similar to, but much smaller than Earth's aurora. Charged particles channeled by the magnetic field toward the polar regions may create very faint emissions as they interact with atoms in Mercury's thin exosphere. As we move through the most recent portions of Mercury's history, human technology begins to reveal the planet's secrets. Ground-based telescopic observations provide the first detailed views of Mercury's surface features, revealing a heavily cratered world that immediately suggests an ancient surface shaped by intense bombardment. Radio telescope observations detect thermal emissions from Mercury's surface, confirming the extreme temperature variations predicted from the planet's lack of atmosphere and proximity to the Sun. These observations also provide the first evidence for Mercury's unusual rotation period and its 3-to-2 spin-orbit resonance. The space age brings unprecedented opportunities to study Mercury in detail. The first spacecraft to visit Mercury is Mariner 10, which makes 3 flybys in the mid-1970s. These encounters provide the first close-up images of Mercury's surface, revealing the Lobate scarps and other tectonic features that indicate global contraction. The space age brings unprecedented opportunities to study Mercury in detail. The first spacecraft to visit Mercury is Mariner 10, which makes 3 flybys in the mid-1970s. These encounters provide the first close-up images of Mercury's surface, revealing the Lobate scarps and other tectonic features that indicate global contraction. Mariner 10 also discovers Mercury's magnetic field, a completely unexpected finding that revolutionizes understanding of the planet's interior structure and evolution. The presence of an active magnetic field indicates that Mercury's core is at least partially molten, despite the planet's small size and presumably rapid cooling rate. The spacecraft observations reveal that Mercury's surface is more complex than previously thought. In addition to the heavily cratered terrain expected from telescopic observations, Mariner 10 discovers smooth plains that indicate volcanic activity occurred after the main bombardment period ended. Ground-based radar observations during this period make the surprising discovery of highly reflective deposits in Mercury's polar regions. These deposits are located in areas that should be permanently shadowed and extremely cold, suggesting they may be composed of water ice or other volatile materials. The discovery of possible ice deposits on Mercury, the planet closest to the Sun, represents one of the most unexpected findings of planetary science. The deposits are likely delivered by cometary impacts and preserved in cold traps, where sublimation rates are extremely low. As our journey through Mercury's timeline approaches the present day, the planet continues to evolve through gradual processes. Space weathering slowly modifies surface materials, occasional impacts create fresh craters, and the ongoing cooling of the interior may still drive small amounts of tectonic activity. The modern era demonstrates Mercury's role as a natural laboratory for understanding planetary processes under extreme conditions. Its proximity to the Sun, unusual bulk composition, and lack of atmosphere create a unique environment that helps scientists understand how planets evolve and respond to different environmental conditions. The modern era demonstrates Mercury's role as a natural laboratory for understanding planetary processes under extreme conditions. Its proximity to the Sun, unusual bulk composition, and lack of atmosphere create a unique environment that helps scientists understand how planets evolve and respond to different environmental conditions. As we move beyond the present moment in Mercury's timeline, we enter the realm of prediction and scientific modeling to understand how this remarkable world will continue to evolve over the next billions of years. The forces that have shaped Mercury throughout its history will continue to operate, though their relative importance may change as conditions in the solar system evolve. Mercury's immediate future, meaning the next few 100 million years, will likely see continued gradual change rather than dramatic transformations. The planet's geological evolution has largely stabilized, with most major processes now operating at very slow rates compared to the dramatic events of its early history. The ongoing cooling of Mercury's interior will continue to drive global contraction, though at ever-decreasing rates. New lobate scarps may still form as the planet accommodates its shrinking interior, but these features will be smaller and less dramatic than the major scarp systems created billions of years ago. Mercury's magnetic field faces an uncertain future as the planet's core continues to cool. The dynamo mechanism that generates the field depends on convection in the liquid iron core, which becomes less vigorous as thermal gradients decrease with continued cooling. Eventually, Mercury's magnetic field may weaken to the point where it no longer provides meaningful interaction with the solar wind. The loss of magnetic field protection would alter Mercury's interaction with the solar environment. Without a magnetosphere to deflect charged particles, solar wind bombardment of the surface would become more intense and uniform, potentially changing the composition and structure of the exosphere and affecting space weathering processes. Space weathering itself will continue to modify Mercury's surface materials throughout the planet's future evolution. The processes that have darkened and altered surface minerals over billions of years will continue operating, gradually homogenizing surface compositions and modifying the optical properties of surface materials. Impact cratering will persist as a surface modification process, though at the very low rates that have characterized recent geological time. Asteroid and comet impacts will occasionally create new craters and refresh small areas of Mercury's ancient surface. But these events will become increasingly rare as the solar system continues to clear itself of debris. The polar ice deposits discovered in permanently shadowed craters face various possible futures depending on long-term changes in Mercury's orbital and rotational characteristics. If Mercury's obliquity changes significantly over millions of years, areas currently in permanent shadow might receive direct sunlight, causing the sublimation and loss of volatile deposits. Conversely, if Mercury's thermal environment remains stable, the polar deposits might persist for billions of years, slowly accumulating additional material from rare cometary impacts while gradually losing mass through various sublimation and sputtering processes. Mercury's exosphere will continue to evolve as surface composition changes through space weathering, and the planet's interaction with the solar wind varies with changes in magnetic field strength. The balance between processes that create and destroy the exosphere may shift over time, leading to long-term changes in its density and composition. As we extend our view to the distant future, billions of years from now, more dramatic changes become possible. The Sun itself will evolve throughout this time, potentially creating entirely different environmental conditions for Mercury and the other inner planets. Over the next billion years, the Sun will gradually increase in luminosity as part of its normal stellar evolution. This enhanced solar output will increase the temperature of Mercury's surface, potentially affecting space weathering rates and the stability of polar ice deposits. The increased solar wind flux may also enhance sputtering processes and alter exosphere dynamics. Looking even further ahead, Mercury faces potential orbital evolution driven by various long-term gravitational effects. Tidal interactions with the Sun, perturbations from other planets, and relativistic effects may gradually alter Mercury's orbital characteristics over billions of years. General relativistic effects are particularly important for Mercury due to its proximity to the Sun and its elliptical orbit. The perihelion advance predicted by Einstein's theory of general relativity continues to operate, and over extremely long timescales, these effects could contribute to orbital evolution. The long-term stability of Mercury's 3:2 spin-orbit resonance depends on various factors including orbital evolution and internal structure changes. If the resonance were to break, Mercury might evolve towards synchronous rotation, fundamentally altering its thermal environment and surface processes. In the very distant future, 5 to 7 billion years from now, Mercury will face the ultimate challenge to its existence, the Sun's evolution into a red giant star. As the Sun exhausts its hydrogen fuel and begins burning heavier elements, it will expand dramatically, potentially engulfing the inner planets. Even if Mercury avoids being directly consumed by the expanding Sun, the dramatically increased solar luminosity and stellar wind during the red giant phase will create environmental conditions unlike anything in the planet's previous history. surface temperatures may rise high enough to melt rock, and any remaining atmosphere or exosphere will be completely stripped away. The red giant phase represents a fundamental transition point in Mercury's evolution. If the planet survives this phase, it will enter an entirely different environmental regime when the Sun eventually sheds its outer layers and becomes a white dwarf star. In the white dwarf era, Mercury would orbit a much smaller, dimmer star that gradually cools over trillions of years. The planet's surface would freeze as solar heating becomes negligible, and any geological processes driven by solar interactions would cease. Mercury would enter a long phase of gradual cooling and thermal equilibration. Throughout these distant future eras, Mercury's role as a record of early solar system history becomes increasingly important. The planet's ancient surface preserves information about conditions during the first billion years of solar system evolution, making it a valuable archive of processes that operated when all the planets were young. Even in scenarios where Mercury's surface is dramatically altered or the planet is destroyed, the scientific knowledge gained from studying it contributes to our understanding of planetary evolution and the diversity of worlds that can exist in different stellar environments. The study of Mercury's long-term evolution also provides insights into the fate of other rocky planets orbiting close to their parent stars. Throughout the galaxy, countless rocky worlds exist in similar high-temperature, high-radiation environments. Mercury serves as a prototype for understanding how such planets evolve and what surface conditions they might maintain over billions of years. Mercury's unique characteristics, its large iron core, thin silicate shell, lack of atmosphere, and extreme thermal environment, represent one possible outcome of terrestrial planet formation under specific conditions. The lessons learned from Mercury's evolution help scientists predict the characteristics and evolution of similar worlds around other stars. As our journey through Mercury's timeline extends into these speculative future eras, we see how the planet's story connects to broader questions about planetary habitability, the diversity of world types in the universe, and the ultimate fate of rocky planets in stellar systems. The extreme conditions that have characterized Mercury throughout its history, from its formation in the solar furnace to its current existence as an airless world with wild temperature swings, demonstrate the remarkable range of environments in which planets can exist and evolve. Throughout our journey across Mercury's timeline, we have witnessed how this small world serves as a natural laboratory for understanding fundamental processes that operate on all terrestrial planets. Mercury's extreme environment and unique characteristics make it an invaluable subject for planetary science research and comparison with other worlds. Mercury's formation history provides crucial insights into the early evolution of the inner solar system. The planet's high metal content and the evidence for a giant impact that stripped away much of its original mantle help scientists understand the violent processes that shaped all the terrestrial planets during their formation. The collision that likely created Mercury's unusual composition represents an extreme example of the impact processes that affected all inner planets during their early history. Earth's moon is thought to have formed from a similar giant impact, while Mars shows evidence of hemispherical crustal differences that may also result from a major collision. By studying Mercury's response to this catastrophic event, scientists gain insights into how planets can survive and evolve after experiencing such extreme trauma. The fact that Mercury retained a substantial atmosphere of iron vapor for millions of years after the impact, and that it managed to continue accreting material to reach its current size, demonstrates the resilience of planetary formation processes. Mercury's thermal evolution provides a unique perspective on how small rocky planets cool and differentiate over billions of years. Unlike larger planets that retain internal heat for much longer periods, Mercury's small size means it has progressed further along the cooling curve than Earth or Venus, showing us what the future may hold for larger terrestrial worlds. The planet's global contraction, recorded in the lobate scarps that crisscross its surface, represents the most dramatic example of planetary-scale tectonics, driven purely by thermal evolution. While Earth's plate tectonics are driven by ongoing heat production and convection, Mercury's scarps show what happens when a planet cools and shrinks without the complicating factors of atmospheric processes or active volcanism. Mercury's magnetic field presents one of planetary science's most intriguing puzzles and success stories. The discovery that such a small planet could maintain an active magnetic field challenged theories about planetary magnetism and led to new understanding of how planetary dynamos can operate under different conditions. The weakness of Mercury's magnetic field compared to Earth's, combined with its different structure and behavior, helps scientists understand the range of magnetic phenomena possible on rocky planets. This knowledge is crucial for evaluating the magnetic environments of rocky exoplanets and their potential habitability. Mercury's surface composition, revealed through decades of spacecraft observations and ground-based studies, provides insights into the diversity of rock types that can exist on terrestrial planets. The planet's low iron content in surface rocks, despite its iron-rich interior, demonstrates how planetary differentiation can create surface compositions quite different from bulk planetary composition. The discovery of sulfur-rich volcanic deposits on Mercury's surface was completely unexpected and has led to new understanding of how volcanic processes operate under different planetary conditions. The high sulfur content may reflect Mercury's unique formation history and bulk composition, showing how different starting materials can lead to different types of geological processes. Space weathering processes on Mercury operate in a more extreme environment than anywhere else in the inner solar system. The combination of intense solar wind bombardment, extreme temperature variations, and lack of atmospheric protection creates surface modification processes that are more intense than those operating on the Moon or asteroids. Mercury's space weathering teaches us about the fundamental processes that alter planetary surfaces throughout the solar system. The darkening and chemical alteration of surface materials by solar wind implantation, micrometeorite bombardment, and thermal cycling help scientists interpret observations of other airless bodies and understand how their surfaces have evolved. The planet's exosphere represents an extreme example of planetary atmospheric physics. Mercury's tenuous envelope of sodium, potassium, and other atoms demonstrates how planets can maintain atmospheres through non-thermal processes, even when traditional atmospheric retention is impossible. The seasonal and orbital variations in Mercury's exosphere provide insights into the complex interactions between planetary surfaces, magnetic fields, and stellar environments. These processes are relevant to understanding atmospheric loss from Mars, the Moon's thin atmosphere, and the atmospheric environments of rocky exoplanets orbiting close to their parent stars. Mercury's polar ice deposits represent one of the most surprising discoveries in planetary science. The presence of water ice on the planet closest to the Sun demonstrates the importance of local environmental conditions and shows how volatile materials can be preserved even in seemingly hostile environments. These deposits provide insights into the delivery of volatiles to the inner solar system and the conditions necessary for their preservation. The discoveries at Mercury have implications for understanding water and other volatiles on the Moon, asteroids, and other small bodies throughout the solar system. The study of Mercury's impact cratering record provides crucial information about the early bombardment history of the inner solar system. The planet's well-preserved ancient surface serves as a fossil record of conditions during the first billion years of solar system evolution. By comparing crater populations on Mercury with those on the Moon, Mars, and other bodies, scientists can reconstruct the bombardment history that affected all inner planets. This information is crucial for understanding when conditions became suitable for life on Earth and how impact processes affected planetary evolution. Mercury's orbital dynamics and rotational evolution provide insights into tidal interactions and spin-orbit coupling under extreme conditions. The planet's 3:2 spin-orbit resonance is the most extreme example of tidal locking in the solar system, demonstrating how gravitational forces can control planetary rotation over long timescales. The study of Mercury's orbital evolution helps scientists understand similar processes operating on rocky exoplanets orbiting close to their parent stars. Many such worlds are likely tidally locked or in spin-orbit resonances, and Mercury provides the best laboratory for studying these phenomena. Mercury's role in testing Einstein's theory of general relativity cannot be understated. The planet's orbital precession provided one of the first confirmations of general relativity and continues to serve as a testing ground for theories of gravity and spacetime. Modern precision measurements of Mercury's orbit contribute to ongoing tests of fundamental physics and help scientists search for deviations from general relativity that might indicate new physics. The planet serves as a natural laboratory for studying gravitational effects under conditions more extreme than those available on Earth. The technological challenges of exploring Mercury have driven innovations in spacecraft design and mission planning. The extreme thermal environment near the Sun requires specialized heat shields, thermal management systems, and orbital mechanics that push the boundaries of space technology. These technological developments have applications beyond Mercury exploration, contributing to our ability to study the Sun, develop solar power systems, and potentially explore other high-temperature environments throughout the solar system. Mercury's scientific value extends beyond planetary science to include solar physics, fundamental physics, and astrobiology. The planet's interaction with the solar wind provides insights into stellar-planetary interactions, while its extreme environment helps define the limits of planetary habitability. As we continue to explore Mercury through ongoing and future missions, each new discovery adds to our understanding of planetary formation, evolution, and the diversity of worlds possible in the universe. The planet continues to surprise scientists and challenge theoretical models, demonstrating that even the most extreme environments can preserve important scientific information. As we approach the current era in our journey through Mercury's timeline, human technology reaches the point where detailed exploration of this distant world becomes possible. The challenges of reaching and studying Mercury have driven some of the most innovative achievements in space exploration, revealing secrets that could never be discovered through ground-based observations alone. The first successful mission to Mercury begins in the early 1970s, when NASA launches Mariner 10, a pioneering spacecraft designed to study both Venus and Mercury using a complex gravitational assist trajectory. This mission represents humanity's first close-up look at the innermost planet, and fundamentally changes our understanding of Mercury's characteristics. Mariner 10's journey to Mercury demonstrates the orbital mechanics challenges inherent in exploring the inner solar system. Reaching Mercury requires not just enormous amounts of energy to change orbital velocity, but also sophisticated trajectory planning to avoid being trapped by the Sun's powerful gravitational field or destroyed by intense solar radiation. The spacecraft makes 3 successful flybys of Mercury in 1974 and 1975, each encounter providing new perspectives on the planet's surface and environment. The mission's cameras reveal for the first time the heavily cratered nature of Mercury's surface, immediately suggesting an ancient world that has preserved a record of early solar system bombardment. The discovery of lobate scarps during these early flybys provides the first evidence for Mercury's global contraction. These distinctive cliff-like features, unknown on any other terrestrial planet, indicate that Mercury has undergone substantial shrinkage as its interior cooled, a process that helps explain the planet's unusual geological evolution. Perhaps most surprising of all Mariner 10's discoveries is the detection of Mercury's magnetic field. Prior to the mission, most scientists expected Mercury to lack any magnetic field due to its small size and presumably solid interior. The discovery of an active, though weak, magnetic field revolutionizes understanding of planetary magnetism and Mercury's internal structure. The magnetic field detection indicates that Mercury's interior is more complex than previously thought, with at least a partially molten core capable of generating a dynamo magnetic field. This finding has profound implications for understanding how planetary magnetic fields form and evolve, particularly in small rocky worlds. Mariner 10's thermal infrared observations confirm the extreme temperature variations predicted for Mercury's surface. Dayside temperatures exceeding 700 Kelvin contrast with nightside temperatures below 100 Kelvin, demonstrating the effects of Mercury's lack of atmosphere and its slow rotation rate. The mission also provides the first detailed measurements of Mercury's exosphere, detecting sodium and other atomic species in the planet's tenuous atmosphere. These observations reveal that Mercury maintains its thin atmosphere through ongoing interactions between its surface and the space environment. However, Mariner 10's orbital constraints mean that only about 45% of Mercury's surface is imaged during the 3 flybys. Large portions of the planet remain unmapped, leaving many questions about Mercury's global characteristics and geological diversity unanswered for decades. Ground-based observations continue to provide important discoveries during the intervening years between Mariner 10 and the next Mercury mission. Radar observations from Earth reveal the surprising presence of highly reflective deposits in Mercury's polar regions, areas that should be among the coldest places in the inner solar system. These radar-bright deposits are located in permanently shadowed areas near Mercury's poles, where temperatures may be cold enough to preserve water ice and other volatile materials. The discovery challenges assumptions about Mercury's thermal environment and suggests that even the planet closest to the Sun can harbor frozen water. Spectroscopic observations from Earth gradually reveal details about Mercury's surface composition, indicating an unusually low iron content in surface rocks despite the planet's iron-rich interior. These observations suggest that Mercury's surface composition is quite different from that of other terrestrial planets, possibly reflecting its unique formation history. The next major milestone in Mercury exploration comes with NASA's Messenger mission, launched in 2004 on a complex trajectory that includes multiple gravity assists from Earth, Venus, and Mercury itself before entering Mercury orbit in 2011. This mission represents the first attempt to orbit Mercury and conduct comprehensive studies of the planet's characteristics. Messenger's journey to Mercury takes over 6 years and demonstrates the technological challenges of operating spacecraft in the inner solar system. The spacecraft requires sophisticated thermal protection systems to survive the intense solar radiation near Mercury, along with precise navigation and communication systems that can operate reliably at high temperatures. The orbital phase of the Messenger mission begins in 2011 and continues for over 4 years, providing unprecedented, detailed observations of Mercury's surface, interior, magnetic field, and exosphere. The mission maps the entire planet's surface for the first time, revealing the complete global distribution of geological features. Messenger's comprehensive mapping reveals that Mercury's geological diversity is much greater than previously thought. In addition to the heavily cratered terrain and smooth plains identified by Mariner 10, the mission discovers extensive volcanic deposits, complex tectonic features, and evidence for a more dynamic geological history than expected. The mission's magnetic field measurements provide detailed information about the structure and behavior of Mercury's magnetosphere. Messenger reveals that the magnetic field is highly dipolar but offset from the planet's center, suggesting unusual conditions in Mercury's core and providing new constraints on models of planetary magnetic field generation. Compositional measurements by Messenger confirm that Mercury's surface is enriched in sulfur and other volatile elements relative to other terrestrial planets. These observations support models for Mercury's formation that involve high-temperature processes and possible volatile loss during the planet's early evolution. The mission's discovery of water ice and other volatile deposits in Mercury's polar regions confirms the earlier radar observations and provides detailed mapping of these unexpected reservoirs. The deposits are likely delivered by cometary impacts and preserved in permanently shadowed crater floors, where sublimation rates are extremely low. Messenger's observations of Mercury's exosphere reveal a complex, dynamic atmosphere that varies with the planet's orbital position, solar activity levels, and seasonal changes. The mission identifies multiple processes that contribute to atmospheric production and loss, including solar wind sputtering, thermal desorption, and micrometeorite vaporization. The mission also provides detailed gravity measurements that reveal information about Mercury's internal structure. These measurements confirm that Mercury has a very large iron core relative to its size, supporting models for the planet's formation through a giant impact or other processes that removed much of its original silicate mantle. As Messenger's mission draws to a close in 2015, the spacecraft conducts increasingly low-altitude observations before ultimately impacting Mercury's surface. The final months of the mission provide the highest resolution images and most detailed compositional measurements ever obtained of Mercury's surface. The wealth of data returned by Messenger keeps scientists busy for years, leading to numerous discoveries about Mercury's formation, evolution, and current characteristics. The mission fundamentally changes our understanding of Mercury and demonstrates that even the most extreme planetary environments can be successfully explored with appropriate technology. Building on Messenger's success, the European Space Agency and the Japan Aerospace Exploration Agency launched the Bepi-Colombo mission in 2018. This ambitious mission consists of 2 spacecraft designed to study Mercury from different perspectives and with complementary instrument suites. Bepi-Colombo's journey to Mercury takes 7 years and includes multiple gravity assists to achieve the complex trajectory required to enter Mercury orbit. The mission demonstrates continued advances in spacecraft technology and thermal protection systems needed to operate in Mercury's harsh environment. The Bepi-Colombo mission arrives at Mercury in 2025, beginning a new era of detailed Mercury exploration. The 2 spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, study different aspects of the Mercury system with unprecedented detail and precision. The Planetary Orbiter focuses on surface composition, geological processes, and the planet's interior structure, while the Magnetospheric Orbiter studies Mercury's magnetic field, exosphere, and interactions with the solar wind. Together, the 2 spacecraft provide the most comprehensive study of Mercury ever undertaken. Bepi-Colombo's advanced instruments provide new insights into Mercury's formation and evolution, building on the foundation established by earlier missions. The mission's high-resolution imaging reveals surface features at scales never before achieved, while advanced spectrometers provide detailed compositional mapping of the entire planet. Looking toward the future, Mercury exploration will likely continue to push the boundaries of space technology and scientific understanding. Proposed future missions might include sample return attempts, long-duration surface operations, and coordinated multi-spacecraft studies of Mercury's environment. The technological challenges of Mercury exploration continue to drive innovations in thermal protection, power systems, and communication technologies. These advances have applications beyond Mercury science, contributing to solar probe missions, Venus exploration, and the development of technologies for operating in extreme environments throughout the solar system. As our exploration capabilities advance, Mercury will likely reveal additional surprises that challenge our understanding of planetary formation and evolution. The planet's role as a natural laboratory for studying extreme planetary processes ensures its continued importance in planetary science research. As our journey through Mercury's timeline brings us to the modern era of astronomical discovery, the The study of our innermost planet takes on new significance in the context of exoplanetary science. The thousands of planets discovered orbiting other stars include many worlds that likely share characteristics with Mercury, making our solar system's innermost planet a crucial template for understanding planetary diversity throughout the galaxy. The discovery of exoplanets has revealed that rocky worlds orbiting very close to their parent stars are among the most common types of planets in the galaxy. These hot super-Earths and ultra-short period planets exist in environments even more extreme than Mercury's, with orbital periods measured in hours or days rather than Mercury's 88-day year. Many of these close-orbiting exoplanets likely experience surface conditions that make Mercury's environment seem moderate by comparison. Planets like Kepler-78b orbit their stars in just 8.5 hours, experiencing surface temperatures that exceed 2000 Kelvin, hot enough to vaporize rock. These worlds represent extreme examples of the type of environment that Mercury has successfully navigated for billions of years. Mercury's survival and evolution in its challenging orbital environment provides crucial insights for understanding how rocky planets can exist and evolve under intense stellar irradiation. The planet's geological processes, atmospheric interactions, and thermal evolution serve as a baseline for predicting the characteristics of similar exoplanets. The processes that have shaped Mercury's composition and structure, including possible giant impacts, mantle stripping, and high-temperature formation conditions, may be even more common and extreme in other planetary systems. Young star systems often contain more debris and experience higher impact rates than our solar system did during its formation. Mercury's magnetic field generation provides important insights for understanding magnetic fields on close-orbiting exoplanets. The interaction between planetary magnetic fields and intense stellar winds affects atmospheric retention, surface bombardment rates, and potentially even the long-term survival of planetary atmospheres. Exoplanets orbiting very close to their stars often become tidally locked, with one hemisphere permanently facing the star, while the other remains in eternal darkness. While Mercury is not tidally locked, its 3:2 spin-orbit resonance provides insights into how tidal forces affect planetary rotation and the resulting temperature distributions. The extreme day-night temperature contrasts that characterize tidally locked exoplanets may be even more severe than Mercury's already dramatic temperature variations. Understanding how Mercury's surface materials respond to thermal cycling helps scientists predict the geological processes and surface evolution of these tidally locked worlds. Mercury's exosphere formation and maintenance processes are highly relevant to understanding atmospheric dynamics on close-orbiting exoplanets. Many hot super-Earths likely maintain tenuous atmospheres through similar processes: surface sputtering, thermal desorption, and volcanic outgassing, while losing atmospheric material through thermal escape and stellar wind stripping. The discovery of water ice in Mercury's polar regions has implications for volatile preservation on exoplanets. Even worlds in extremely hot environments may harbor cold traps where volatile materials can be preserved, potentially affecting their long-term evolution and even their habitability characteristics. Mercury's space weathering processes provide a framework for understanding surface evolution on airless exoplanets. The combination of stellar wind bombardment, micrometeorite impacts, and thermal processing that continuously modifies Mercury's surface operates on countless airless worlds throughout the galaxy. The techniques developed to study Mercury's surface composition from orbit and through remote sensing have direct applications to exoplanet characterization. Spectroscopic methods, thermal observations, and magnetic field measurements used to study Mercury help develop the observational strategies needed to characterize exoplanetary environments. Mercury's role in testing theories of planetary formation extends to understanding how rocky planets form in different stellar environments. The conditions that led to Mercury's unusual composition and structure may be common in planetary systems around different types of stars, or in systems with different disk compositions. The orbital dynamics that govern Mercury's motion, including general relativistic effects and tidal interactions, become even more extreme for exoplanets orbiting closer to their stars. Mercury serves as a laboratory for understanding these gravitational effects and their influence on planetary evolution. Studies of Mercury's thermal evolution and interior structure provide templates for modeling the internal dynamics of exoplanets with similar compositions and thermal environments. The cooling and contraction processes that have shaped Mercury's geology likely operate on many rocky exoplanets, though potentially at different rates and with different outcomes. Mercury's interaction with solar wind and stellar magnetic fields provides insights into star-planet interactions that are crucial for understanding exoplanetary environments. The magnetic reconnection, particle acceleration, and atmospheric sputtering processes observed at Mercury operate in more extreme forms around many exoplanets. The technological challenges overcome in exploring Mercury have contributed to the development of observational techniques and theoretical models used in exoplanet research. Heat-resistant instruments, precision navigation systems, and thermal modeling approaches developed for Mercury missions have applications in studying other extreme planetary environments. Mercury's geological diversity, revealed through detailed spacecraft observations, suggests that even planets formed under extreme conditions can develop complex geological histories. This finding has implications for predicting the surface conditions and evolution of rocky exoplanets in similar environments. The discovery that Mercury has maintained geological activity much longer than expected based on its small size provides insights into the factors that control planetary geological lifetimes. This understanding is crucial for evaluating the potential for geological processes on exoplanets of different sizes and compositions. Mercury's magnetic field strength and structure, compared to those of other terrestrial planets, help establish scaling relationships for predicting magnetic field characteristics on exoplanets. These predictions are important for understanding atmospheric retention and surface conditions on rocky worlds throughout the galaxy. The seasonal and orbital variations observed in Mercury's exosphere provide insights into the atmospheric dynamics of planets with highly elliptical orbits. Many exoplanets have more extreme orbital eccentricities than Mercury, making the planet's atmospheric variations a valuable baseline for understanding more extreme cases. Mercury's survival in its challenging environment for over 4 billion years demonstrates the resilience of rocky planets under extreme conditions. This longevity suggests that similar planets throughout the galaxy may maintain stable surface conditions over geological timescales, potentially allowing for complex chemical evolution even in seemingly hostile environments. The study of Mercury's polar regions and their unique thermal environments provides insights into the diversity of microenvironments that can exist on a single planet. This understanding is relevant to evaluating the potential for diverse surface conditions on exoplanets, including the possibility of localized habitable regions on otherwise extreme worlds. As observational capabilities continue to advance, the detailed characterization of Mercury achieved through decades of spacecraft missions serves as a benchmark for the level of understanding that may eventually be possible for nearby exoplanets. The progression from basic detection to detailed surface mapping illustrates the observational advances needed to fully characterize exoplanetary environments. Mercury's role in the broader context of comparative planetology extends beyond our solar system to encompass the full diversity of rocky worlds throughout the galaxy. The planet serves as a crucial data point in understanding the range of possible outcomes for terrestrial planet formation and evolution under different conditions. The ongoing study of Mercury continues to reveal new aspects of planetary science that have direct applications to exoplanet research. Each new discovery about Mercury's formation, evolution, or current characteristics adds to our understanding of the processes that shape rocky worlds throughout the universe. Our extraordinary journey through 4.5 billion years of Mercury's history draws to a close, but the story of this remarkable world continues to unfold with each orbit around our Sun. We have witnessed a planet forged in fire, sculpted by violence, and shaped by forces that operate nowhere else in our solar system with such intensity. From its catastrophic birth through giant impact to its current existence as a world of extremes, Mercury's timeline reveals fundamental truths about planetary evolution and the incredible diversity of environments that can exist in the universe. This small world, racing around the Sun every 88 days, carries within its cratered surface and metallic heart a complete record of the processes that shaped our entire solar system. Throughout our journey, we have seen how Mercury challenges our understanding of what planets can be and how they can evolve. Its oversized iron core speaks to the violent collisions that characterize the early solar system. Its global contraction scarps reveal how planets respond to internal cooling over billions of years. Its tenuous exosphere demonstrates that even the most extreme environments can maintain dynamic atmospheric processes. The patterns that emerge from Mercury's long history, the interplay between internal evolution and external bombardment, the balance between heating and cooling, the persistence of geological processes, even in the most challenging conditions, provide insights that extend far beyond a single planet. Mercury serves as a natural laboratory for understanding the fundamental physics and chemistry that govern all rocky worlds. Perhaps most remarkably, Mercury's story demonstrates the power of gradual change operating over vast timescales. The planet we observe today bears the accumulated effects of billions of years of slow cooling, thermal cycling, impact bombardment, and space weathering. Each process operates at rates that would be imperceptible over human lifetimes. Yet together, they have transformed a young, hot world into the ancient, scarred planet we know today. Mercury's relationship with the Sun defines every aspect of its character and evolution. The intense solar radiation that makes Mercury one of the most challenging environments in the solar system also powers the processes that maintain its exosphere and drive its surface chemistry. The gravitational effects that lock Mercury in its 3:2 spin-orbit resonance create the complex thermal environment that shapes its geology. This intimate dance between Mercury and the Sun continues today and will persist for billions of years into the future. As the Sun evolves and changes, Mercury will respond, adapting to new conditions while preserving the record of its ancient past. The planet's future evolution will be shaped by the same fundamental forces: gravity, thermal physics, electromagnetic interactions that have governed its history since formation. The exploration of Mercury by human spacecraft has revolutionized our understanding of this distant world and demonstrated that no environment is too extreme for human ingenuity to study and comprehend. Each mission has revealed new surprises and challenged existing theories, showing that even the most thoroughly studied planets can still hold secrets. Mercury's scientific importance extends beyond planetary science to encompass solar physics, fundamental physics, and the search for life in the universe. The planet's role as a testing ground for Einstein's theory of general relativity continues to contribute to our understanding of gravity and space-time. Its interactions with the solar wind provide insights into the processes that affect all planets orbiting close to their stars. In the context of exoplanetary science, Mercury takes on new significance as a prototype for understanding the thousands of hot, rocky worlds discovered orbiting other stars. The processes that have shaped Mercury, thermal evolution, tidal interactions, space weathering, volatile loss, operate in even more extreme forms on many exoplanets. As we stand at this moment in Mercury's timeline, we can appreciate both the planet's ancient stability and its ongoing evolution. The major geological provinces established billions of years ago remain largely intact, yet subtle changes continue as space weathering modifies surface materials. Thermal cycling stresses crustal rocks, and rare impacts add new craters to the ancient terrain. Mercury's timeline also reminds us of the dynamic nature of our solar system and the cosmic forces that continue to shape all planetary environments. The planet exists in a state of constant interaction with its space environment, bombarded by solar wind particles, heated and cooled by solar radiation, and perturbed by gravitational forces that slowly but persistently alter its orbit. The story of Mercury is ultimately a story of survival and adaptation. This small world has endured conditions that would destroy less resilient planets, maintaining its geological integrity while continuously evolving in response to changing conditions. Its persistence demonstrates that planets can thrive in a wide range of environments, adapting to challenges that initially seem insurmountable. Looking toward the future, Mercury will continue to serve as a crucial laboratory for understanding planetary processes under extreme conditions. Future missions may reveal additional surprises about its composition, internal structure, or evolutionary history. Each new discovery will add to our understanding of how planets form and evolve throughout the universe. The timeline of Mercury teaches us that every planet has a unique story shaped by its formation history, orbital environment, and internal characteristics. No two worlds evolve in exactly the same way, yet common physical processes create recognizable patterns that help us understand planetary diversity throughout the cosmos. Mercury's eternal dance with the Sun continues as it has for billions of years, a testament to the stability of gravitational systems and the persistence of planetary environments. Each 88-day orbit carries the planet through temperature extremes that would challenge human imagination. Yet Mercury endures, slowly evolving while preserving the record of its remarkable history. As our journey through Mercury's timeline concludes, we are left with an appreciation for the incredible complexity and beauty of planetary evolution. From cosmic dust to a world of fire and ice, Mercury's story encompasses some of the most extreme processes operating in our solar system, while revealing the fundamental principles that govern all planetary environments. The closest planet to our Sun will continue its ancient orbit, carrying forward the legacy of 4.5 billion years of evolution, while slowly, imperceptibly, continuing to change in response to the cosmic forces that have shaped it throughout its long and remarkable history. Thank you for joining this extraordinary journey through the timeline of Mercury. The story of our solar system's innermost world, past, present, and future, continues with each moment, a reminder of the dynamic universe we inhabit and the incredible diversity of worlds that exist within it.